This is 3.7, polynomial and rational inequalities. So a lot of the things that we're going to do here may seem very familiar. This is just one step further. We've already talked about polynomials, solving polynomial equations using synthetic division and graphing them. And we also talked about the end behaviors. We also talked about rational equations. So now what we're going to be talking about is rational and polynomial inequalities. So the same steps, what we're going to be doing, move all terms to one side, especially on inequalities. That's really what you want to do. And then factor the polynomials, finding the zeros, and then find the intervals. Remember, we tested the intervals between those zeros to see if it goes up or down. Make a table or a diagram of doing that, especially if it says to graph. That helps you understand the problem as well. And then it says to solve the actual problem, and that will help you determine which way the graphs go in each interval. So let's look at our first example. So the first thing we're going to do is move everything over to one side. So here we have 2x cubed plus x squared minus 13x plus 6 is greater or equal to 0. And then what we're going to do is factor that. And once you factor that, you're going to get x minus 2, then you're going to get 2x minus 1, and then x plus 3. Now notice the zeros. Remember what we kind of said is, kind of pretend that that's not greater than. For right now, pretend it's not greater than, pretend it's equal to. So we can see the zeros, x equals 2, x equals 1/2, and x equals -3. So and imagine that on a number line. So we have 1/2, there's 1, 2, 1, 2, 3. So we have negative 3 right here as a 0. We have 1/2 as a 0, and we have 2 as a 0 on a number line. So notice you can see the intervals. You have this interval over here from -infinity all the way to -3, and then you have -3 all the way to 0. Not 0, 1/2. And then you have 1/2 all the way to 2, and then you have the interval from 2 to infinity. Okay, so those are the 4 intervals, and what we're going to do is test those intervals to see if it's, if it's a true statement. Also keep in mind that we're referring to, I just drew the x line, but this is really just the x line and the y line, and we're trying to determine the graph of it, and depending on which interval is true. So if we started testing certain points, so if you tested a point, in each interval, you're going to end up seeing that this interval works in between this interval, and you're going to see that this interval works in between here and there. Like for instance, if you plug in 0, like if you test this point right here, 0, you're going to end up getting something that's positive, and that's greater or equal to 0. And so you see that interval works, and you would see that this interval does not work, this interval does not work, and this interval does work. So you could see the final answer, because we're trying to find out what will satisfy it. So we have the intervals -3 to 1/2, and that's the union. These actually should be brackets right here, just because of this right here. So that's all I need to do. It says solve it, so you're trying to find out what solutions. And also keep in mind graphically what's happening. So if I graph this function, so literally if I graph this, graph that polynomial, remember the end behaviors on this? So the end behavior, like if I look at these zeros, the end behavior, it's going to go up here and it's going to go down here. And notice that it's going to go up here and go back down here. Well, notice what it's talking about is when is it going to be greater than 0? And notice greater than 0 is in this interval. And in that interval, it's above the x line. So it's positive. So you could You could solve it like what we're doing, but I'm just, this is the interval notation of the answer, but you can also look at it graphically to be able to answer the question. So let's look at another example. So here we have example 2, and our very first step, again, you follow the process of getting everything over to one side. So 3x to the 4th minus 2x to the 3rd minus x squared minus 12x, and then minus 4. And it's less than 0 on this one. So again, start thinking graphically if it's less than 0. So we're looking for something specifically lower than the x line. So that's something to consider here. And when you got to factor this, and factoring, you might have to use synthetic division, and to be able to get to the answer. So you're gonna end up getting x minus 2, 3x plus 1, and x squared plus x plus 2. And then that's the factoring of it. And then you notice you're going to get a 0, x equals 2 from the first one. You're going to get x equals negative 1/3. And then this one right here, if you actually solve this using the quadratic, you're not going to get any real zeros. You're going to end up getting some imaginary numbers. So the intervals, if you look at the intervals on a number line, so let me draw a number line here. So we have 2 as one of the zeros, and we have negative 1/3 as one of the zeros as well. And then the other ones, again, are going to be imaginary. So these are my only 2 real roots that I'm going to be doing. And then you start testing the signs in these intervals, right? So start testing a sign in this interval from negative infinity all the way to negative 1/3. And then you have this interval of negative 1/3 all the way to 2. And then you have another interval from 2 to infinity. So if you start testing those intervals, you're going to see the only interval works is this right here. And so you can see the final solution, the interval is negative 1/3 to 2. And if you look at the graph of this, remember this is to the 4th power and it's positive. So you know the end behaviors are going up, and this is going to be going down below. So I mean the graph actually looks like this. Again, we're talking about XY axis here. So the graph confirms the interval where it's going to be lower than 0, and you can see that on the graph as well. All right, so let's look at an example of one problem solving a rational inequality. So notice the rational inequality, we talked about that in the previous lessons. We have to find, this is not a polynomial, is a continuous drawing, a function. So when you start talking about rational, then you're going to have vertical asymptotes and horizontal asymptotes that you have to worry about. So it's not going to be continuous, but we can still solve it and then look at the diagram as well to confirm our solution. So the first thing we got to do is solve it. And remember the steps that we did is bring everything over to one side, especially with those inequalities. So we're going to have 1 minus 2x over x squared minus 2x minus 3. And then that's minus 1 is greater than 0. Now, just to refresh your memory, these are both fractions. You got to get a common denominator. And so we're going to literally make this as, this one's not going to change. So we're literally just going to make this x squared minus 2x because it's 1. So we're just going to put it over itself. So that way they have a common denominator. And just keep in mind, you got to use that distributive property to be able to do that. So you're going to end up with x squared minus 2x minus 3 on the bottom. And then on the top, you're going to end up with negative. Well, let me go ahead and, let me just go and do this. So you're going to end up with negative x squared. That's negative x squared. And then when you do negative times negative, that's positive 2x. That's going to cross out with this 2x. And then negative times negative for the 3 is positive 3 plus the 1 is 4. So you're going to end up with that. And then what we're going to do is, this is still greater than 0. Now, if we factor this, we're going to end up getting 2 minus x and 2 plus x on the top. And on the bottom, we're going to get x minus 3 and x plus 1. Now, from this, you can see a couple things. You can see that the zeros in the denominator, you can see what they are. So we have, if I highlight these, so x, you can see what those are. So you can see what x cannot equal 3, and x cannot equal negative 1. So those are going to be my vertical asymptotes if you think of it, what the graph looks like. Okay, so we have vertical asymptotes at positive 3, and we have it at negative 1. So that's what the graph's going to look like as far as asymptotes. Now, if you remember the rule to find the horizontal asymptote, if these are these exponents, if these exponents are the same, then really it's just the coefficients divided by one another. So it's just really negative 1 is the horizontal asymptote. So we have a horizontal asymptote right at negative 1. So the graphs, we have to test the intervals in between those asymptotes, the vertical asymptotes, and we're going to test it to kind of see what the graph looks like. So once we start testing points in there and start graphing, we're going to end up getting a graph that looks like this. Notice it crosses right at negative 2, which is going to be helpful up here if you look at that. It's also going to be crossing at 2, 0 in the middle here, which again is going to be very helpful. And then when you start graphing numbers down here, and if you start testing points over here, you'll see the graph looks like that. So notice what we're trying to find is, if you look at the original function, we're looking, well, actually this is the original function. So we're trying to find out when it's going to be greater than 1. Just looking at the graph, you can see it, but you should also test the actual points to see, into the original problem and see if it's actually, where is it greater or equal to 1. So I want you to notice the graph, because these two are, equivalent to each other, but graphically, you're trying to find out where it's going to be greater than 0 above the x line. And so if you notice from right here at negative 2, and all of a sudden it starts going above 0. So we have at negative 2, and it keeps going closer and closer to negative 1. And remember, it never actually reaches negative 1, so that's a parenthesis, an open interval. And then notice above 1 right here from 2, above 0. Graphically we're trying to do that, above 0. And so above at 2, and it goes all the way to 3, but it never actually can reach 3. So that would be a closed interval. So all of this closed and open interval union set is what I'm trying to find out where it's going to be greater or equal to 0. And again, you can always test points. If you test points in that interval, that's what we kind of did to even graph it. If you test points in this interval and that interval, you can see that it will fit to the original problem. I just wanted to show you graphically where it exists as well.